I'm going to go ahead and start off, like I said in the previous lecture, I want to start off each lecture with just a quick review of a pretty intense problem from 0.4. Just because this stuff, there's a lot of rules going on, and the best thing to do is practice it as much as possible. Okay. So this problem is not going to be relevant for what we're covering today. It's just a quick review of section 0.4 or section P4. Okay, so we want to simplify this thing. This is 3x squared, y to the 8th, all over 48, x to the 4th, z to the 5th, all raised to the -1/2. All right, so one of the first things that might stump you here is there's a lot going on, so you know some stuff you might be able to do, but you don't know if it's the smart thing to do, right? So you might be stalling there. Oh, okay, am I good? My camera made a noise. All right, I think I'm good. So you might be stalling out there, and also just trying to remember all the rules, you know. So and how to write down. Like if you have an idea about something you could do, but you're not sure how to write it down. So let's go over that. So I'm going to solve it over here in red with one way you might solve it, and then I think I'll solve it another way. All right, first thing you want to do here is simplify inside the parentheses. Can I simplify these numbers? Can I simplify these x's? Can I simplify the y's or the z's? So I'm going to, in step 1, I apologize if you can hear that truck outside. It should be gone soon. Okay, so question is, can I simplify 3 over 48? And the answer is yes, 3 does go into 48. In fact, it's 3 times 16 is 48. So I'd write a 16 in the denominator. And if I need to, if I cancel everything out of the top, because I've canceled the 3 now, right? By saying 3 over 48 is 1 over 16. If I cancel everything in the top, then I will need to put a placeholder of 1 up there. But maybe there will be other stuff left over up top so that I won't need that placeholder. So I'll leave it blank for now and see if we do need it. So now x squared and x to the 4th, those will cancel as well, right? I have x squared, 2 x's up top, 4 in the bottom. That's the easiest way to think about it. If you cross out the common ones, you're going to cross out everything up top and you'll be left with 2 in the bottom. And in fact, that's all that can be simplified because there are no other y's or z's anywhere else. So I'll just copy the z's down, and in fact, the y's will be left up top. All right, so already a lot cleaner just by trying to clean up inside the parentheses. All right, so now the next thing I'm going to do is deal with this negative out here. And the way I'm going to deal with that negative is I'm not going to change any of the signs on the exponents inside, even though they're all positive anyways, right? 8, 2, and 5, they're all positive. All I'm going to do is I'm going to, whoops, that's still 1/2. I'm going to use up that negative to flip everything in here. So that means this stuff goes up here and the y to the 8th goes down there. If any of these exponents were negative, like say if the 8 was negative, I would still flip it to the bottom. It would just be in the bottom now. So all that happens when I use up this negative on the outside is the entire fraction inside just flips upside down. All right. Now I'm going to apply the 1/2 exponent to each of these, cut each of these in half. Okay, so we know it can be written as a root, right? Remember last time we looked at or whatever time it was, we looked at how this can be written as a root, but I'm going to solve that in the second way I solve that. We'll look at it that way. So I'm going to distribute this exponent of 1/2 to every single one of these numbers. So I'll just stick it on the 16 there, 16 raised to the 1/2. Then I have x squared raised to the 1/2, and I have z to the 5th raised to the 1/2. So I'm just sending this 1/2 to every single, so all 4 of these numbers inside, the 16, the x squared, the z to the 5th, and the y to the 8th. All right. Now I'm going to use the rule that says if I have exponent raised to exponent, I multiply them. So that allows me to clean up the x squared raised to the 1/2. 2 times 1/2 is just 1, so that's giving me x to the first. Z to the 5th to the 1/2 is the same as 5/2. So real quick little side fraction stuff. So if I have 5 times 1/2, that's the same as 5/2, but that's the same as 2 1/2. So I can write that z to the 5/2 as z squared. Remember that's the whole number is the exponent there, and then an extra z to the 1/2, just splitting it up because in the last step I am going to write them as radicals if possible, so I'm splitting it up there. All right, so that's the z to the 5/2 with my side work there. The 2, the whole number 2 is the exponent there, and then the remaining fractional part is right there, splitting it into two across two terms there. And then the last one is easy, y to the 8th raised to the 1/2. Multiplying there gives me a nice whole number. I don't need to worry about that fraction stuff with the y. All right. Now what I'm going to do is at this point I pretty much have to write them as radicals. I can't get too much farther without just finally accepting that I need to go ahead and write these 1/2 as radicals. So 16 to the 1/2 is going to be square root of 16. Just recalling our rational exponent rules. The 2 is the index, so that means it's a square root. Remember, we suppress the 2, the notation, but technically there's a little 2 right there. And the 1 becomes the numerator, or rather the numerator of 1 becomes the exponent in here. But again, if it's just a 1, you don't need to explicitly write it. And then I have times. I'm going to put a dot here just to show that these things are attached by multiplication now. So everything here is attached by multiplication. And then finally, my square root of z at the back. So the x to the first is there, the z squared is there, and then there's my square root of z. And no problem bringing down y to the 4th. Square root of 16 is 4. So I've got 4, and I'll go ahead and drop the dots in between now because it's not necessary. And there we go. That's it at this point. The last thing we should know, and this is hard to remember when you do it this way, but what we should know is that we technically took an x squared and square rooted it and got an x out, right? So we took a variable out of a square root, and its exponent is odd. Its exponent is technically a 1, which is odd. So we do need to wrap that x in absolute values. We don't need to wrap the z squared or the y to the 4th because their exponents are even. Okay, so only when you have a square root or a 4th root, some kind of even root, you pull a variable out. If its exponent is odd, then you have to wrap that variable in absolute values. All right, so I would call this like the exponent way, where you basically, this is as if you were trying to avoid dealing with the radicals until the very last minute. So now let's go back through this and solve it as if you treated it like a radical from this step. So the first two steps of simplifying inside the parentheses, which I did here, and then dealing with that negative by flipping everything inside, I would still, those are good first steps. So I'll rewrite that. I have 16 x squared z to the 5th over y to the 8th, all raised to the 1/2. Now this is where I'm going to deviate from here. So in this previous, in the red, I went ahead and distributed the 1/2 to each one of these variables. But here I'm going to say, oh, that 1/2 means square root. So I'm literally going to have a giant square root of this entire fraction. Oops. And then I know that by our radical rules, our rules dealing with radicals or roots, I can go ahead and split this up. And now I can deal with this however I want to deal with it. I can split each of these up individually. Remember, at this point, you might be more comfortable saying, okay, I know the square root of 16 is 4. No problem there. How many groups of 2? can I get out? You know, if I have x squared, that's a single x. How many groups of 2 can I get out of z to the 5th? Well, there would be 2 with 1 left over. So this is where, if you feel more comfortable thinking of it this way, like in this kind of grouping way, then you might like this better. And how many groups of 2 can I get out of y to the 8th? Well, that would be 4. Oh, and I need absolute values because of everything I said earlier, right? Pulling a variable out of an even root and its exponent is odd, then we need those absolute values. Okay, so that's a very involved problem. This is like one of the most intense ones on the homework. That something like this wouldn't be on a test. It's just too intense. But there you go, 2 different ways to solve it. This way seems easier, right? You don't have to, you really got to know your exponent rules back here to do this way. And then you really get into some weirdness when you say the z to the 5/2 is this, right? It's just, it starts to get weird. You can do it this way, but this way is probably a little bit more intuitive. All right. Let's get back to what we were doing, which is talking about factoring. So we were talking about factoring. What did we cover? Factoring by grouping, factoring by difference of squares, and now let's talk about some other special factoring formulas. So let's see, just as practice, because we can never get enough of this, let's do factoring by grouping. Let's factor, let me think for a moment. Let me write something down. I want to give us a good one. X 5. Okay, so minus 3x minus. Okay. All right, so we're going to factor this by grouping. So recall that we still set up a little chart to start off with, kind of like the same way we did with the easiest form of factoring. And we don't write 15 here, right? And typically, or with a leading coefficient of 1, you would just write the 15 here. But since that's not a leading coefficient of 1, it's a 2, we need to account for that. And what we do is we take the product of that leading coefficient with the constant, and that's what sets up our little chart there. And then the middle term, that linear term, still goes here. And now we need to think of 2 numbers such that their product gives a positive 30 and their sum gives a negative 13. So we think about that. I'm going to press forward. I might get you guys involved in the latter parts of this lecture, but I want to push through this review section because we've already done this. So this is a review of what we did last time. So the numbers would be negative 10 and negative 3. Good. What we do is we use these numbers to split that central term. So I'm going to have negative 10x. And does it matter which order I put them in? No, it doesn't. We do have to remember that little thing I said about dealing with a negative. If this term is negative, which it is in this case, then we have to be careful in our next step when we group these things into 2 terms of 2 groups of 2 rather. I'm going to say plus, and I'm going to include that negative inside that second group there. So I've taken this thing, I've set up my chart, I found the numbers that work to build this little chart. I've used those numbers to split the central term. And now I've grouped, and I've noted that since this term here is negative, I want to include that negative inside my parentheses. So I need to stuff a little plus sign there. So basically treating it as, instead of minus 3x, I'm treating it as plus negative 3x, which is perfectly fine. And now I'm going to factor out the greatest common factor from this term, which will be a 2x, leaving me with x minus 5. And I'm going to factor out the greatest common factor out of this term. And I know that they should end up matching. Like what I'm left with here should also be an x minus 5. So that should give you a hint that I'm going to pull out a 3. And also that it should be a negative 3 in order to get the signs right. Right, so I pull a negative 3 off a negative 3x, leaving me with an x. Pull a -3 off of 15, leaving me with a -5. All right. Now I'm going to factor this whole term, x minus 5, out of this expression here. So I'm going to pull x minus 5 out. And that's going to leave me with the little remaining pieces, 2x minus 3. That's it. That's how we factor by grouping. And if you wanted to check, you can take this, multiply it out, and confirm that you'll get back here, which you will. You will, because we factored it right. Okay, so that's factoring by grouping. Let's talk about factoring a difference of squares, which I asked you to look at. So I'm going to go quickly through this and assume that you reviewed factoring a difference of squares. So consider an expression, a polynomial expression, I'll just say an expression of the form a squared minus b squared. Okay. We can factor this. We have a formula for this, and I'll explain the formula and then we'll practice it, into a plus b times a minus b. So where is this coming from? Well, consider like x squared minus 36. What if we just tried to factor it sort of like with our little chart thing, kind of the way you would factor the very first things I gave you, which were like x squared plus 7x plus 12. So you set up your little chart, you say the constant term goes here, but what is the linear term? What is that central term, the term attached to x? Well, technically it's a 0. 0. So if I am looking for the sum of two numbers that add to 0 that also multiply to give -36, they're definitely both going to be a 6, and one of them is going to be negative. And then I can, since this has a leading coefficient of 1, I can jump straight to the factored form, which is x plus 6 times x minus 6, which is exactly what the formula gets to. The formula says you don't need to do all this. If you recognize it as a difference, meaning a subtraction, of two perfect squares, so x squared is a perfect square, and 36 is a perfect square, then you can jump straight to the factored form. So let's do a more difficult example. What example were we on? I think 5. So this is in 0.6. Okay, so our example 5 is going to be to factor 9x squared minus 49y squared. So a bit more involved, but the point is they're both still perfect squares. Both of these terms are perfect squares, and it's a difference. So what we want to do is figure out what is the square root, right, of each of these terms. In other words, if 9x squared is playing the role of the a squared, then what is the a? And if 49y squared is playing the role of the b squared, then what is the b? So let's see, I'm going to call on somebody. Let's see, just first in the way I'm seeing you here, Taylor, if a squared is 9x squared, what would a be?
If ax squared is 9x squared, what would a be?
Yeah. Think of something like each one of these is a perfect square. Think of what do you have to square in order to get a 9?
3.
Yep. And then what do you have to square in order to get x squared?
1.
1x, right, in x.
Mm-hmm.
Because what is x? If I square x, then I get x squared. So it tells you in its name like what the root should be. So that means that'll be 3x. And similarly, so now b squared is 49y squared. So b will be 7y. Cool. So now we have our a and b. So we have 3x plus 7y, and 3x minus 7y. There we go. So once we set up, or once we recognize them as a difference of perfect squares, which it's pretty much always going to be easy to recognize them because they only have two terms and it's a difference, and usually perfect square numbers will jump out at you. So then your job is to figure out what the a and b are, like what the roots of each of these terms are, and that's actually what gets plugged in here. Okay, cool. Now let's look at other special forms besides difference of squares. Let's look at perfect square trinomials. Oh, I spelled square wrong. Okay. So I'm looking at perfect square trinomials, means they have three terms. Okay, so what is a perfect square trinomial? It's just one of the trinomials we've been looking at. Like you've seen several trinomials now. That first thing I gave you here, 2x squared minus 13x plus, that's a trinomial because it has three terms. But we're looking at trinomials that will factor into a perfect square. And what does that mean? So we are looking at trinomials that will factor into this form. Some term plus some term all squared, or some term minus some term all squared. In other words, the factor that we get when we factor them, it's going to be repeated. So I'll give you an example. And by the way, it's different from difference of squares, right? A difference of squares is one term is positive and one term is negative. They exactly match, but it's positive, negative. This is going to be one where they exactly match, but they're both positive or they're both negative. So what are these going to look like? So for example, consider x squared plus 6x plus 9. Okay, if we went about this the traditional way, we say two numbers that multiply to give a 9, two numbers that add to give a 6. Thinking, and we get 3 and 3. So we're seeing a repeat. They're both positive 3s. So that means down here, if I jump straight to the factored form, I get this. But the point is they're repeated, so I can stuff them together and say this is just the same as x plus 3 all squared. All squared, meaning it's this term times itself. Okay, that term times itself. So that's one example of a perfect square trinomial. This is right here. How do we recognize them? So how do we recognize perfect square trinomials? How do we recognize perfect square trinomials? We look for, what does this have? A constant term that is a perfect square number, like 9. So for instance, 9 is a perfect square number. Okay, so that's one of the triggers for looking for these perfect square trinomials. If you see the back number is a perfect square, you might start thinking, oh, this might factor really cleanly into something like this. Also, that's not the only thing though. There's something special about the middle number and the linear coefficient, the 6 in this case, the linear coefficient. If you like, you can just call it the middle number, the number attached to x. Is, now this is going to be a little bit more of a mouthful, but twice the root of the constant. So what does that mean? That means whatever the roots of this perfect square constant back here, in other words, it's a 9, so what's its root? Its root is 3. If this central number is double that 3, which it is, right, in this case, then you have a perfect square trinomial. If the root of this, which is 3, if you double that and you get the middle term, that means you have a perfect square trinomial. Okay. And we can see that over here, it's getting doubled, right? 3 plus 3 is 6. All right, so let's look at another example and let's try and factor it without having to fall back on the chart. So what if we have x squared plus 10x plus 25? So first we can say, and set up my little parentheses here. This is kind of hopeful that it will be perfectly factorable, which it is. And Maya, what do you think it would factor into? Because it is a perfect square trinomial. We see that 25 is a perfect square and its root is 5. And if you double that, you get 10. So Maya, what would this trinomial factor into?
Oh, 5.
And what would each of the factors look like?
So it would be like x plus 5.
And then another one, right?
Yeah. I thought it would be x minus 5.
That's if you have a difference of squares.
Oh. All right.
So remember, these perfect square trinomials, the point is they're repeated. So this is why we call them a perfect square trinomial, because after you factor it, you can write it as a perfect square. So this is why it's called a perfect square trinomial. Okay. And let's do another one with a difference, and then we might move on. So let's say, the back number has to be a positive perfect square. I'll just say 49, and this will be 14x. So here, if I asked you guys to factor x squared minus 14x plus 49, this is what should happen. You should say, oh, that 49 is a perfect square with a root of 7. And in fact, if I make the 7 negative and I double it, then I get negative 14. So this is a perfect square trinomial. This is a perfect square trinomial, and it's going to factor simply into x minus 7 times x minus 7. In other words, it's going to factor into x minus 7 squared, because it's a perfect square trinomial. It's a perfect square trinomial because it factors into a nice compact little thing. So these are like analogous to perfect square numbers. Like 25 is a perfect square number because it factors into 5 squared. This trinomial, is a perfect square trinomial because it factors into a term squared. It's just, so they're analogs to perfect square numbers. It's just, of course, the terms that build the polynomial are a bit more complicated than just a number because there's a lot more going on here, right? Okay. And then the next special factoring formulas are sums and differences of cubes. I don't want to do that here. If we need it, we'll have a formula for it, but I don't want to spend time on that. So let's see. Factoring sums and perfect squares. Okay, we did that. Factoring by grouping. Okay. So I want to move into chapter 1 now. Let me get caught up in my book here. Chapter 1 is equations and graphs. All right, sure. It says equations and graphs, and we are going to graph some, but most of our graphing will be done of functions. We'll be graphing functions, and that'll come later in chapter 2. But we can graph, we can talk about graphs of equations. That's no problem. And you've already done that, like linear equations. You've graphed linear equations before. But let's start with section 1, which is the coordinate plane. So just becoming comfortable with the coordinate plane. Okay. Get some coffee. Okay, so the coordinate plane is just that picture you've seen 100 times with a x-axis and then a perpendicular y-axis. And you know that the way we navigate around this Cartesian coordinate plane, or just coordinate plane, the way we navigate it is we give coordinate pairs that tell you how to move around the coordinate plane. So for instance, the point 3 comma -4, the point 3 comma -4, which I'll show as a red dot, I'll put over here. That'll be 3 to the right down the positive axis, x-axis. So somewhere along here at x equals 3, and then down at -4 for the y value. So there we go. There's that point 3 comma -4. So that's the x value at 3 and the y, and the y value at -4. So that's how we navigate around the coordinate plane. We'll do another one just because. Let's say the point 0 comma 5, the point 0 comma 5. So the point 0 comma 5 is at x equals 0. Now x equals 0, if this is 1 and over here this is -1, then 0 is here. So that means the point is somewhere along the x-axis. I mean, sorry, the y-axis, the y-axis. If x is equal to 0, then the point is somewhere along the y-axis. And where is it along the y-axis? Well, it should be up at 1, 2, 3, 4, 5. There's that point. Okay, let's talk about the structure of the coordinate plane, just some basic names for different pieces of it. This area here, where both x and y are positive, is called quadrant 1. So we call this Q1. So Q1 with a Roman numeral 1 is quadrant 1. So quadrant just means like something has been split up into 4 pieces. So you probably already guessed there's going to be 4 quadrants, right? It is quadrant 1. And what can I say about quadrant 1? Both x and y, both x and y are positive. I'll just say plus for positive. Okay, now going counterclockwise, we have quadrant 2 is quadrant 2. And let's see, Aviana, what would be positive and negative in quadrant 2?
X would be negative and Y would be positive.
Yes, good. Okay, so up here we have negative x values because this is the negative x-axis, so we've moved this way, so x is negative and y is still positive because we're up above the x-axis. So anything above the x-axis is going to be positive for the y value. Okay, now moving on to quadrant 3 is quadrant 3. They're both negative here. That's right. And y is negative. So quadrant 3, they're both negative. Oh, I'm out of paper. Go through a lot of paper for these online lectures. That's okay. All right, then we have quadrant 4, of course, the last quadrant here. Quadrant 4. And x is positive in quadrant 4 and y is negative. Okay. Another way to sum all of this up with a picture, you may have seen this kind of picture before, is you have the you have the plane here, the coordinate plane, and you might see this like plus plus up there. So saying x and y are positive. Then over here we have negative plus, down here we have negative negative, and over here we have positive negative. So every combination showing up. Now there are 4 more pieces to the coordinate plane, and that's the areas, or rather the lines in between these quadrants. So I said, quadrant 1 is where they're both positive, but what if, it's on an axis? Like if I said for this green point I drew, which quadrant is this point in? Well, that would be not a good question because it's not in a quadrant. It's on the positive y-axis. So let's see, this thing is the positive y-axis. And then once you pass this point where it starts to become negative, this is the negative y-axis, And just because the picture is starting to get cluttered, I'm going to change colors just so you can see it a bit better. This is the positive x-axis. This piece here is the positive x-axis. And this piece over here is the negative x-axis. And if you hear me say just the x-axis, then I mean the entire thing. So they're both parts of the x-axis, but if you want to be specific, this is the positive x-axis, this is the negative x-axis. And then the point in the very center, right here, the point 0, 0, also has a special name. It's called the origin of the plane, of the graph, of the coordinate plane. Yeah, I'll say coordinate plane. All right, cool. So that's how we graph points. Quick review of graphing points, right? I'm kind of assuming you already know how to graph points. And just you may not have seen this before about the quadrants and the signs of each x and y in each quadrant. But this is just the basic structure of the coordinate plane. So now let's talk about a couple things we can do with points on the coordinate plane. Some stuff we can do with points on the coordinate plane. I'll say with 2 points. All right. Okay, what can we do? We can do a lot, but one of the first things you might learn when you learn about numbers, like real numbers, is how to find how far away they are from each other. In other words, how far away is 3 from 5, and you just subtract, right? You say 5 minus 3 is 2. That's how far those numbers are away from each other.
What title did you write up there?
Some stuff we can do with 2 points on the coordinate plane. Is that what you asked?
Yes, sir.
Okay, cool. Okay, so how do we find the distance between 2 points if they are not on one axis? Like if 2 points are on in one dimension, then you just like if you know the point at 5 and the point at 3, you just subtract, find that distance to be 2. But what if they are 2 random points out here and then another one here? How do we find the distance between the points? So this is one of the things we can do. Given 2 points, can we find the distance between them? So, and I apologize if you hear that garbage truck outside. It should be gone in just a few seconds. So I'm going to call this distance D. How can we find the distance between 2 points? And in fact, let me go ahead and label these points, and I'm going to be generic about it. If I want to just call them generic points, I will call, they're both XY points, so I'll call this one X sub 1 and this one Y sub 1. So when I say sub, I mean like in the subscript position. So that's X with a little 1 down in the subscript position, comma, Y with a little sub 1 in the subscript position. And then this point up here, x2 comma y2. So all this is this saying this is a point xy. We'll call it point 1. So I'm subscripting them with a 1. And then a point 2, just calling it the second point, and they're still xy, and I'm just subscripting them with a 2. Okay. So these are super generic points. I've drawn them both in the first quadrant just because we can. Like I could put the picture over here or here or here. It doesn't really matter. I'm just drawing it there just because it looks nice there. All right, but they are very generic points. They could be negative, they could be 0. Okay. So how can I find the distance between these 2 points, between the points, between 2 points, namely x2 comma y2 and x1 comma y1? Okay, how can I find the distance between these points? Well, I can consider a right triangle with this distance D, some distance here. Now, if these points, okay, given these points, what would the length of this segment be here? Wouldn't this just be the difference in the 2 x values? In other words, if this point was at x value of 3, so just ignore the y value. If this was a 3 and this was a 5, to find just the horizontal distance between the points, you would just subtract those 2 x values. You would just subtract those 2 x values. And similarly, does anyone have an idea about what this side would be, just the vertical distance between the 2 points? Mikira, any idea? Or Nikita?
Would it be the y2 minus y1?
Yes, that's right. The vertical distance will be the difference in those y values. Okay, nice. Okay, now Pythagorean theorem tells us, and remember this is a right triangle. I've forced a right triangle out of this little picture and labeled the 2 sides. The Pythagorean tells us that if we square this side and square this side and then add them, then we get this side squared. So we're almost done. We are almost about to solve, we're almost about to solve for the distance. By the Pythagorean theorem, we have that x2 minus x1 all squared, so this entire side squared. This is like, if you recall the Pythagorean theorem, a squared plus b squared equals c squared. This entire thing is like a, so I'm squaring the whole thing. So that's like a squared plus b squared, which is the entire other leg, should be equal to the hypotenuse squared, which is d squared. Hypotenuse is d here. And then when we clean it up, what we like to do is we like to completely solve for d, which means if it's squared and I want to solve for d, I'll just throw a square root over this entire thing, here. In other words, I'm saying, let me flip it around so that the d is on the left side because it looks better that way. So I'm taking this thing, d squared is x sub 2 minus x sub 1. The difference in the x value squared, I'm just rewriting the formula right now, plus the difference in the y value squared. Okay, I'm going to square root both sides, the entire thing, and that effectively gets rid of the square on the on d here, right? Now the right side is going to have to look ugly like this. This is the formula. So d now is equal to this giant, maybe scary looking formula, but hopefully from its construction here, from the Pythagorean theorem, that might help you to remember where it comes from and the motivation for it. I won't often prove things like this. This is a proof. This is like a math proof, a visual math proof, though really this is the way you would do it anyways. But anyway, I won't often prove stuff in this class. A lot of times I'll just ask you to take my word for it. But this is pretty straightforward, and you've seen the main piece of this proof is the Pythagorean theorem, which you've seen before. So kind of can't really show you this formula without showing you that it really is just the Pythagorean theorem in 2 dimensions. That's what's happening here. This is the Pythagorean theorem, but on a coordinate plane, so in 2 dimensions. Okay, so let's practice it. Let's call this example 1. Let's put all this together. Let's say, so this example will probably eat up the rest of our time, and that's okay. Given the points, and let's just name them in case we need to talk about them. We'll call the first point A, -3, -4, and B, I'm going to make it work out to be a not nice answer. So let's say, okay, I'm sorry, I'm thinking 1, 0. Given these points, what do I want you to do? We're going to A, identify which quadrant or axis they lie in, or on. If it's an axis, we would say they lie on the axis. If they're in a quadrant, we would say they lie in the axis. We're going to graph them, and we could do part B first if we want. In fact, I probably will do that, and also find the distance between. All right. Let's graph them first. I put A, maybe I should have put graphing them as part A. It's fine. All right, so I'm going to have my graph. I already should have a feeling for how big this graph should be, like how far apart my tick marks should be, just based off of the points themselves that I need to graph. They're only going out to -3, -4, so I don't need, I'll probably just stop at 5 tick marks on each axis here. Oh, ran out of room there. That's okay, I'm not going up the y-axis. Okay. So the point A is at -3 for x, which puts me over here. -3 is right here, so -1, -2, -3, and then down -4. 1, 2, 3, 4. So it should be lining up here. Let me get, sorry, lining up with this and this. So somewhere right about there, maybe a little bit further over. That's point A. Point B is at 1, 0. So for X, it's over at 1. And for Y, it's 0, meaning it doesn't move up. It's not positive. It doesn't move down. It's not negative. It's right at 0, meaning it's on the X-axis. It's on the X-axis. B. Okay. So which quadrant or axis do they lie on? Well, I've partially already given it away. Which quadrant is A in Kimberly?
Quadrant 3.
Good. Quadrant 3, good. And B is also on the positive x-axis. If I wanted to be specific, I'll say positive x-axis. It wouldn't be wrong to say B is on the x-axis, but if we want to be real specific, we'll say the positive x-axis because it's on this side. If it was over here, it would be the negative x-axis. All right, now the real part of this problem, the tricky part, or the more involved part, is finding the distance between them. Real quick, rewriting the formula just for our convenience. Okay, so when I plug this in, I just need to, the first thing I need to do is pick which is going to be 0.2 and which is going to be 0.1. So what I mean by that is, like, if I have point A is -3, -4, you might find it helpful to do something like this, to label them up above as x1, y1, and so that's the first point. Both of the subscripts are 1, and this point as x2, y2. Oops, x2, y2. Just to help when you're getting used to this formula, so you don't get mixed up, you know. So both of these should have subscript of 1 because they're from the first point, and these should both have subscript 2. Now, could you pick them the other way around? Yes, yes. As long as your work stays organized, you're going to end up with the same answer. But I'm picking the point A to be 0.1 and the point B to be 0.2. Okay, so setting up here, x2 is 1, then minus x1 is -3, so I'm going to have some extra parentheses introduced here to deal with these negatives. Okay, now I've got plus y2 is 0, and then minus, and then parenthesis for the -4, close that, and then square it. All right. Okay, just some integer arithmetic coming up. So 1 minus -3 is 1 plus 3, which is 4. So I have 4 squared plus, and then 0 minus -4, that turns into a plus. 0 plus 4 is 4. Okay, squared. Now, following my order of operations, I know I need to square these and then add them. So that's going to be 16 plus 16, which is giving me the square root of 32. Remember, as tempting as it is to split this, because they're both perfect squares, you cannot split around that addition. So I cannot say like, oh, it's just this, you know, I cannot do that, As tempting as much as it would be nice if we could do that, radicals do not allow for splitting around the operations of addition or subtraction. So I have to add them. And then can I simplify this? Yeah, that's square root of 16 times 2, which is the same as square root of 6. Now I can split it around multiplication, see? And then that's going to give me 4 square roots of 2. So long story short, D is 4 square roots of 2, which is some number. By the way, what is that approximately? Because 2, let's see, I'm going to plug it into the calculator, all right, and then times 4. So this is, D is approximately 5 I'll just round to the 10th place, so 7. Does that look right on our graph? Well, who knows? Like, it's at a slant. It's hard to tell, right? It's hard to tell what that distance would be. We got a 5.7, I guess. I mean, if you look at this and say this distance, you know, down the y-axis where A is at -4, right? So this distance is about 4, so it should be a bit longer. if you really got the ruler out, you might be convinced, but the point is this distance formula does all that for us. We don't have to get the ruler out and like measure it and see exactly how long it would be and all that. So there's the distance as an exact answer, 4 square roots of 2, with all those terrible decimal numbers stuffed into the square root of 2. And then if you want an approximation, just pop this into the calculator, 4 times square root of 2, and you'll get, you know, and then you can round and get an approximate answer. Sometimes your distance will work out to be a nice whole number. I purposely made this one not do that so that we could get more practice, right? Okay, so before we go, we got 5 minutes, so let me just talk about what we're going to do next time. We're going to look at midpoint formula, which will be another formula, a lot easier, a lot more straightforward than the distance formula. And that's pretty much going to finish 1.1. And then we'll go straight into 1.2 and try and get as far as we can, hopefully finishing 1.2 next time. So be practicing, try to get that 0.4 homework done. I would not put it off any longer or you're going to start to forget stuff. Be practicing factoring. Like factoring is going to be huge in this class. We will factor all the time. Like pretty much in every single chapter, you're going to need to know how to factor trinomials. So you just cannot get enough practice factoring trinomials. Oh, and before y'all leave, I need to take roll. So let me just glance at who's here. I'll just write down the names. So Taylor Thicklin, Maya Lovelace, Aviana Pruitt, Nikita Lee, Kimberly Owen, Kyria. Okay. All right. If you guys don't have any questions, you are good to go, and I'll see you Wednesday.
Is the distance formula the same thing as for finding the midway point?
Oh, sorry, say that again.
For one of the questions on the homework for the equation and graphs,
Yeah.
it has find the midway point between the points. Could you use the distance formula for that, or is that just a different formula?
It's different, yeah. The midpoint is when you're trying to find, like, see, here's the easiest way for me to. Here's the most straightforward way for me to answer that. Distance between two numbers should be a number, like not a coordinate point, right? It gave us just one number, right?
Mm-hmm.
But the midpoint between 2 points is going to be a new coordinate point. So they are very different formulas, but you'll see next time. It's actually a very easy formula, meaning, well, it makes a lot of sense. You may have trouble thinking about how to do it like on your own, like how would you figure that out? But once you see it, you'll be like, oh, that makes a lot of sense.
Okay.
Okay, I'll see you Wednesday.
All right. Thank you.